Hi, everyone. I think we're going to get started. So I think, Linnea, you're going first. Okay. I think you're muted.
Sorry. Yeah.
Okay, great. We can hear you. So yes, hello, everyone, and welcome back to the LEAP lectures. Today we have our very own Linnea Hawkins. Linnea is a postdoctoral scholar at NCAR and a collaborating researcher at LEAP. Her research interests broadly lie at the intersection of climate, natural resources, and management, with a particular focus on the fostered ecosystems of the Western US. Society relies on the climate mitigation role of forests. However, forests are vulnerable to climate-driven changes in drought frequency and severity, changing fire weather conditions, and management practices and policies. Linnea's research investigates the effects of changing climate conditions on the vulnerability of forest ecosystem, carbon, and water cycling. She uses measurements and models to assess the consequences of climate change on carbon sequestration and water availability for municipal, industrial, cultural, and ecological uses. Linnea received her PhD in atmospheric science in 2019 from Oregon State University, where she developed high-resolution climate projections designed to inform climate adaptation efforts. Linnea also worked with the Oregon Climate Change Research Institute to engage stakeholders in the co-production of science to build climate resistance communities in Oregon. With that, take it away, Linnea. Thanks.
Great. Thanks, Kate. Yeah, so thanks for the introduction. I am part of LEAP, but I sit physically in Colorado where I work at NCAR, and I work closely with Daniel Kennedy, Katie Dagan, and Dave Lawrence here, where we are developing machine learning-based parameter estimation methods for the community land model. And to provide some background and context for motivating this work, we know that there's a lot of uncertainty in the CMIP model projections of the land carbon sink. And this is really critical for understanding the sensitivity of our climate system. So this figure on the left here shows the cumulative land flux, so how much carbon the land takes out of the atmosphere, and the spread across these different CMIP-6 models is on the order of hundreds of petagrams of carbon. And to put that number in some context, the US emits roughly 10 petagrams of carbon in fossil fuel emissions each year. So hundreds of petagrams of uncertainty is really unacceptable. And so we need to start constraining this uncertainty. And the land component of Earth system models is a little bit different from the atmosphere and ocean, where the ocean models are typically dominated by scenario uncertainty out by mid-century or so. The land models are dominated by model structural uncertainty and parametric uncertainty on really long time horizons. So it's critical that we reduce this model uncertainty. And model uncertainty is composed of two parts, right? It's the model structural uncertainty and then the parametric uncertainty. And this work aims at addressing the parametric uncertainty. So we are working with one model, the community land model. It is NCAR's community Earth system model, the land component of the community Earth system model. And we started by just exploring the parametric uncertainty in this one CMIP-6 model. We identified 32 of the most influential parameters in this model and then ran a 500-member perturbed parameter ensemble out through 2100. And the result is that the spread in how much carbon the land takes out of the atmosphere is around 1,000 petagrams, which is on the same order of magnitude as the spread across CMIP-6 models. So this unconstrained parametric uncertainty is really quite large, and we need to develop methods for constraining it. And an obvious choice is to introduce observational constraints during the historical period when we have robust observations. And that allows us to rule out some of these parameter combinations as being implausible. The method that we have adopted for constraining this parametric uncertainty is called history matching. It systematically introduces new observational constraints to rule out regions of the parameter space that are implausible. And I'll walk through this methodology. This first step is to generate a perturbed parameter ensemble. So in the fall, there was a science freeze and there's a new version of CLM. So we started this process over with the latest version, CLM 6. We identified 56 parameters and ran a 1,500 member ensemble. So here's the results of that. I'm showing each ensemble member in gray. The global leaf area is on the x-axis and the global photosynthesis is on the y-axis. And our observational data products and their uncertainty are this on target with the shaded bands. So even though this is a really large ensemble, 1,500 members is extremely computationally intensive to generate, especially for land components. You actually have to spin up every single ensemble member due to the biogeochemical cycling processes. And so even though it's a large ensemble and was computationally expensive, it really doesn't even begin to explore a 56-dimensional parameter space, right? That's like an incredibly sparse sample for a parameter space that with that high of dimensionality. So this is where the machine learning comes in. If we can train a emulator for CLM that's computationally cheap and efficient, we can better explore that parameter space with a cheap version of the model. So effectively what this emulator does is it interpolates between the points that we ran in our perturbed parameter ensemble. So then we get an estimate of the response. That might be the photosynthesis or the leaf area for any given combination of parameters. And then once you have this cheap surrogate model, you can explore that parameter space really robustly. I'm going to spend a few minutes, a quick aside on a few more details of how we developed this emulator, and then I'll come back and describe the rest of the methodology. So to develop this emulator, there's a few really specific challenges that are unique to land models. And one is that they have these plant functional type specific parameters. So a land model represents lots of different plant types, different grasses, shrubs, trees, broadleaf, needleleaf, evergreen trees. And one parameter, such as like the leaf carbon to nitrogen ratio, might actually have a unique value for every different plant functional type. So in that way, it has these nested parameters. Some of them are global parameters, like anything related to hydrology, while other are these nested, and those parameters interact. And having 16 different versions of one parameter really inflates the number of free parameters we have, and it takes it up to hundreds and hundreds of free parameters, which is just an unmanageable amount of parameters to handle. So that's one challenge. Another challenge is that PFTs, these different plant functional types, trees and grasses, they all coexist on any given grid cell, and they compete for water and nutrients below ground. So you can't just tune one of these plant types without it affecting the other plants that live on that grid cell. So there's interactions between the plant parameters. And the third challenge is that our observational products are typically just gridded. And in any given grid cell, there might be multiple plant functional types. And if the gridded data product is just telling me that there's one value for the photosynthesis for this one grid cell, I have no way of disaggregating that to the proportion that came from any one individual plant type. So we spent a lot of time trying to figure out how best to address these three challenges. And I think it was really key to work closely with the domain scientists on this, where we were able to work with model developers and come up with a solution to address these challenges. And the solution we came up with is to divide the world up into these different biomes, where each biome, in any given biome, there's only a few PFTs, plant types, that coexist. So for instance, in the tropics, you might only have 2 or 3 different plant functional types whereas in the Arctic, those don't coexist with any of those tropical plant types. So we worked with the domain scientists to develop these biomes, and then we train a separate emulator for each biome. And in that way, if there's only 3 PFTs, we can treat all of those PFT parameters as independent, and that's, keeps us in a manageable number of parameters. So we have maybe 60 to 80 parameters in that case. And that actually works quite well. We've had quite a bit of success in training the emulators in that for these individual biomes. The tool we're using for this is Gaussian processes, and that's a fairly simple machine learning tool, but it allows you to define your covariance structure. So it works really well in these extremely sparse data environments. And we have a really high dimensional parameter set and only a few training data points. So providing some structure has really improved. We're getting really good results when we provide some covariance structure, and that's why we are choosing the Gaussian processes. So this is our emulator design. It allows us to address all 3 of those concerns. We can tune PFT parameters independently. We are capturing interactions between PFTs on any given grid cell, and we can tune to global gridded data products. And then we're also getting pretty good spatial representation out of our tuning because we're able to tune, the tropics separately from the Arctic, for example. Okay, back to the methodology here. Once we have these emulators trained, we can then take a really dense sample of the parameter space and emulate what we expect that result to be. And so in this way, we can explore the parameter space more robustly. And then we introduce our observational constraints and rule out many of these parameter accommodations as being implausible or not in agreement with historical observations. Then we can resample from the parameter posteriors and run new ensemble members, as the blue points here, and increase our perturbed parameter ensemble with more points that are closer to this observational range. Then we retrain our emulators on this larger ensemble and repeat this process multiple times, and end up with a observationally constrained perturbed parameter ensemble is the goal. So that's the methodology. What this looks like in practice, we started with just an initial wave of that workflow. The first wave, we take a nearly random, evenly distributed sample and run that 1,500 member perturbed parameter ensemble. And that's this blue histogram. I'm showing leaf area on the left, photosynthesis in the center, and total vegetation carbon, which is something like biomass, on the right. In the first wave, we introduced a leaf area constraint. So we're just using the observations of leaf area. And then in the second wave, we introduced this biomass, GPP, and leaf area constraints. And we see that we're getting pretty good results. We're starting to narrow in our ensemble, and it's centering up roughly on our expected observational target. But that's expected for these variables that we're actually introducing observational data for. What's more interesting is how we are constraining variables that we don't actually measure. So here I'm showing that cumulative land carbon sink again, which isn't actually directly measurable. It's usually calculated as a residual of the other aspects of the carbon cycle. So we can't directly measure this, but by introducing these leaf area, biomass, GPP constraints, we are indirectly constraining that cumulative land carbon sink. So this work is still in progress, and we plan to, once we've finished these waves of history matching, we want to extend these simulations out through 2100 under multiple emission scenarios. And then we want to publish this observationally constrained perturbed parameter ensemble, which we think will be quite valuable to the community as for others to start to assess uncertainty in the land carbon sink. And then from there, we want to explore this uncertainty in emissions-driven runs. So typically a climate model is run with prescribed atmospheric CO2 concentrations, but that doesn't allow for a freely evolving carbon cycle. If you have emissions-driven simulations, then there's feedbacks between the land carbon sink and the atmospheric CO2 concentration. Those simulations are going to be extremely expensive because they're coupled and global and emissions driven. So we will have to select just a small subset of our parameter of our observationally constrained perturbed parameter ensemble. And for that, we want to try to sample some of these across some of these axes of uncertainty where there's still not a lot of scientific consensus around such as the strength of the CO2 fertilization effect or what we expect the change in the water use efficiency to be. So we plan to select a small handful of parameter sets that span some of these unique axes of uncertainty and then run those in these emissions-driven simulations. So that's where we're going with this work. But currently, since NCAR is in the middle of a model development cycle, they're getting ready to release CESM3, which will be used in their contributions to CMIP7. Our current focus is on calibrating CLM6. And because after the history matching process, we have trained these really robust emulators of the model, we can use those in a model calibration. So in past development cycles, the land model really has only been hand-tuned because it's too computationally expensive to run these ensembles. So now we can use these emulators in really any traditional calibration workflow. And because we have this computationally cheap version of it. So we're working through this calibration right now, and we hope that we're seeing some early progress, early success, that we can reduce the biases in some of the key variables. And we hope that we'll have a calibrated version of CLM6 for use in CSM3. Okay, so I'll quickly just summarize. The objectives of this work was to first constrain parametric uncertainty in our projections of the land carbon sink, and second, to calibrate the community land model. We're working towards these outcomes, which I expect to be an observationally constrained perturbed parameter ensemble, and we hope that our calibrated version of CLM6 will be used in CSM3. We've also formed a really large community around this work. It's been valuable to other applications in CSM, and the data sets that we have produced in association with this work are being used by other students and postdocs. And we've formulated different interest groups, and we're also leading a calibrated land model intercomparison project, CalMIP. And future directions, I think we need to build out the software a little bit more so that these calibration tools can be more easily accessible and used by the broader CSM community. We also want to assess this uncertainty in emissions-driven simulations. And then lastly, I think moving forward, we want to extend our methodology to be able to work with coupled model where the land and atmosphere are coupled so that we can capture land atmosphere feedbacks during our tuning. So that is where we're going with this work. And if there's time, I'm happy to take questions. Thank you.
Hi, Linnea. Very interesting talk. I have a very basic question about CLM. Do the plan functional types, are they prescribed or do they evolve throughout the simulation?
The fractional area on the grid cell that they exist is prescribed, but the like biomass, their canopy height, the leaf area, how much below ground rooting depth, all those things, those are evolving.
Hi, Linnea. Thanks for the talk. I just have a very basic question. Your output of the emulator, why where you say it's the mean of the biome, can you just describe briefly, like what's the dimension of that? How does that look like? Is it like a global vector that, yeah, just the dimension of it?
Yeah, thanks. This is a really good question. I think where we want to expand in the future. Right now, it's just 1D, right? I have one value for the biome mean LAI. And so we've been trying to improve this. Actually, I might have a slide on this. We've been trying to expand on how we develop those emulators because there's so much equifinality in a biome mean, right? Anytime you take a spatial average, you're not able to capture some of the heterogeneity there. And then on top of that, I'm only trying to tune to the mean climate state, right? I'm not doing any time evolving calibrations yet. So one of the things we're exploring is how might you do temporal and spatial emulation? And then we can set up the emulator something like this, where we have the target is just the grid cell leaf area for any time point. And then you have your parameters, and you might bring in the meteorology and then the site-specific attributes such as the soil properties. So this is a direction we want to go in the future so that our emulators can be time evolving and we can get more spatial information out of them than just that biome mean. I think that's a big limitation of our workflow right now. Thanks for the question.
Great. There is a question online. It says, Linny, I've really enjoyed your talk. Can you expand on what data you're considering to calculate the delta for water efficiency?
So we don't have observations, right? You can kind of indirectly observe the water use efficiency as the total, so just for non-land people, water use efficiency is the amount of water used per unit carbon. And so you could imagine it being the evapotranspiration over the photosynthesis. We don't directly observe transpiration, and so there's no direct measurement of that at the global scale. You can do it at flux towers, maybe with sap flow data. But the way that we would try to see this range in water use efficiency in the modeled ensemble and try to span that model uncertainty in water use efficiency, because I would argue that we don't have good enough observational constraints to limit that delta. I'm open to the idea that we can use site level simulations, site level data, and there may be some other ways of doing that, but there just isn't good data at the global scale, I don't think.
All right, let's give a round of applause again.